Welcome viewer. I am going to start the episode 4 of Electrochemistry 1, and till now we have discussed a lot about the theories of strong and weak electrolyte, like Debye-Heckel theory of a strong electrolyte and the transport number in the last lecture. Now we are coming to discuss about the application of this fascinating area of study and research. The first topic I am going to cover in this lecture is application of conductivity measurement and what are the different types of conductivity titration we can do, and the other application we can definitely look forward is the solubility product of sparingly soluble salt and the ionic product of water. Let us start with the different types of application which we look forward for conductivity and its determination, which can help us in finding that. The first thing that come to a mind is the determination of degree of dissociation. We have already discussed a lot about this, and we have to discuss about the Ka, which is outcome of the degree of dissociation, and then conductometric titration is an important topic to be covered, then sparingly soluble salt and ionic product of water. These are the applications that I am going to cover in this lecture. Let us start with the degree of dissociation. If we look at, we have already talked about the Ostwald dilution law in the last few lectures, which can give you the degree of dissociation, which is a ratio of equivalent conductance by the equivalent conductance at infinite dilution. So, this relationship we have already seen, and which can further lead to the determination of dissociation constant. This is important parameter to know, because there are number of unknown carboxylic acids where we are interested to find out how good it is, how better it can furnish the H plus ion, and we are trying to find this Ka, and this Ka can help in the characterization of unknown carboxylic acid. So, to complete the discussion on the degree of dissociation and the dissociation constant of weak acid, let us try to look at one numerical, that is the molar conductance of 0.01 molar solution of acetic acid was found to be 16.30 into 10 raised to minus 4 Simon meter square per mole at 25 degrees Celsius. The molar ionic conductance of hydrogen and acetate ion at infinite dilution were 349.8 into 10 raised to minus 4 and 40.9 into 10 raised to minus 4 Simon meter square per mole respectively at 25 degrees Celsius. Our aim is to find the alpha or degree of dissociation for this case. If we try to look at the first, we try to find out the lambda infinity of acetic acid. This can only be determined if we have the Kohlrausch law with us, which suggests that the acetate ion and the H plus ion infinite dilution equivalent conductance can be added up, and we get a value that is 390.7 into 10 raised to minus 4 Simon meter square per mole. And the moment we have lambda infinity, we know that degree of dissociation is related with that term. So, equivalent conductance at a given concentration and the ratio with the equivalent conductance at infinite dilution. This two ratio suggested a value of 0.4172, and when we try to convert into a percentage, we get a value of 4.172, which suggests that the dissociation of the acetic acid is 4.172 percentage, and which means that out of 100 molecule 4.172 molecule are able to dissociate. It is a very small number if you try to look at. So, these are a important application if you want to understand unknown acid. One of the important application of conductometric measurement is finding the concentration of unknown electrolyte, and this is based on a principle of that the titration of one of the ion is replaced by the other, and the two ions are definitely having a different ion conductivity, and this bring about a different graph, and equivalence point can be located from the graph if you plot a conductance versus the volume of titrant added. The few thing I would like to add at this point is that this conductometric titration has a edge over volumetric titration, because they can be used with the colored solution, which is not possible when you are using a indicator. The second thing is that they give a more accurate result comparative with the volumetric titration, because we get a equivalence point instead of end point. Now, what are the different type of curves we can get from various type of titration which is possible? The first we will try to look at the titration between a strong acid and a strong base. The acid is taken in a beaker and the base is added from burette. With the help of conductivity meter and conductivity cell, we get a values of conductance which can be plotted on the y axis, and the values of the titrant added can be plotted on the x axis. As we plot these values, we are going to see there is a decrease in the conductance with the addition of the NOH, and after reaching a certain minimum value it began to rise again. So, this is a curve which we say curve we get for a strong acid and strong base. So, what is the reason of getting this such type of curve is that the moment you have HCl in the solution, the H plus ion are very mobile, they can move very faster, they have very high ionic conductance. When they are replaced by the Na plus, which is less mobile, the conductance began to fall down and the H plus is getting consumed in this process in the form of water, which do not dissociate to a larger extent. So, till this the fall is there up to there is a H plus in the solution. After that there is no H plus ion in the solution, the curve began to show a rise, and that is totally due to the presence of free OH minus ion. If you try to look at the another set of experiment which can be performed, when we have a weak acid like acetic acid and a strong base like NOH, we are carrying out the titration of these two species. When we try to plot the curve, we get that initially the curve fall down and then it rises, and then there is sudden rise in the curve. So, our equivalence point is at this juncture where the two curves are meeting at this point, and why there is a this type of shape is there can be explained very well when we look at the equation. We have acetic acid which is a weak acid, it is able to give a less number of ion in the solution, therefore, the conductance has a low value. The moment a NOH is added to it, it forms a salt, sodium acetate salt, and sodium acetate salt being a strong electrolyte can dissociate completely, which is shown by this lower equation. The moment we compare this equation, which suggests that the acetate ion which is there in the solution in excess initially, it is going to suppress the formation of acetate ion further, that is common ion effect is going to play a role. So, what we see in this curve is that the conductance fall down because the dissociation of acetic acid is suppressed further, and as we increase the concentration or the volume of NOH added, the curve began to rise, and this is due to a sodium acetate formation which is a strong electrolyte. After reaching a equivalence point at this juncture, there is a further increase in the conductance which can be assigned to the strong base NaOH OH minus ion. There is also possibility to carry out a strong acid and weak base titration like HCl versus NH4OH. If you look at in the burette, the NH4OH is added and the acid is in the beaker with the conductometric cell dipped in that, and conductance measurement suggests that as the ml of NOH is added, the conductance is falling down. After reaching a limiting value, lowest value, there is no change in the conductance, which can be explained well, because if you have H plus ion in the solution, it is replaced by NH4 ion in the solution, because the H plus will react with OH minus and form water. What remains in the solution is NH4 plus and Cl minus ion. NH4 has less mobility. So, we see a decrease in the conductance of the solution. After reaching a equivalence point, when there is no H plus in the solution, we see a lowest possible value, and when further NH4OH is added in the solution, this show a almost a no change, that can be assigned to the weak dissociation of NH4OH, which is not able to give a large amount of OH minus in the solution. One of the important curve which we can get from conductivity titration is the reaction between the weak acid with weak base, because this titration is not possible with the normal volumetric method, because we do not have any indicator which can show a color change. So, the curve suggests that there is a small dip in the conductance initially, and after that there is an increase in the conductance. After reaching equivalence point, it level off, it become parallel to the x axis. So, the curve is interesting because it has a small hump type of thing in the initial part, that can be explained. If you look at the equation, acetic acid being a weak acid, it forms dissociated and undissociated ion in the solution, therefore, it has a lower conductance. The moment NH4OH is added to that, it forms a salt. That salt is ammonium acetate. Being a salt, it is a strong electrolyte. The moment this two ion which is there, acetate ion in the solution, being a common ion, this suppresses the dissociation of acetic acid further, and initially there is a dip in the conductance, and that can be assigned to the common ion effect. And as the conductance is increasing, which can be assigned to the formation of ammonium acetate, which is a strong electrolyte, and after reaching equivalence point there is no change in the conductance. It is totally due to the weak dissociation of ammonium hydroxide. These methods, conductivity titration, can be used further when we have a mixture of two things, two acids like strong acid and weak acid like HCl and acetic acid. If we want to carry out such type of titration, we have to have a mixture of this. Any known mixture can be determined using this method. If we take a strong acid, there is a fall in the conductance initially, that can be assigned due to the formation of water and the loss of H plus ion from the solution till it reaches the a point known as equivalence point. After that, the weak acid began to dissociate. If you try to look at the two equations we have, the question arises why the weak acid is not dissociating initially. This can be answered if you look at these two equations. HCl being a strong acid is capable of dissociating completely into ions, but acetic acid is a weak electrolyte, it dissociates feebly into acetate ion and H plus ion, and the moment these two are in the mixture, the H plus ion suppresses the formation of acetic acid, acetate ion, and the equilibrium shift in the backward direction. That is the reason till there is H plus ion from HCl, there is no dissociation or contribution from the weak acid. After the consumption of the H plus ion, we get a dissociation of weak acid, and this shows a slight increase in the curve, and that can be assigned to the formation of sodium acetate, and after reaching this point it further increases. If we are using a strong base like NaOH, the strong base show a increase in conductance due to OH minus ion, which is more mobile, and if you are using a base like ammonium hydroxide, the conductance do not show any significant change, and that will be due to the weak electrolyte nature of ammonium hydroxide. If we want to do a titration, precipitation titration to find the concentration, we have to look at two different compounds. One is KCl versus AgNO3. If you look at what we have a silver nitrate in a beaker, and KCl can be added from burette, and conductance is being measured. The moment the KCl is added to the solution, the conductance do not show any change, it is almost parallel to the x axis, and this region is very clear because the K plus and Ag plus have almost similar ionic conductance. The values are 73.52 and 61.92. So, there is a change, but not a significant change, because one K plus is replaced by Ag plus and it continue till the silver nitrate in there in the solution. After that, there is a sudden increase in the conductance, which is due to the K plus ion which is added from the burette. So, this is a very simple method to find out the concentration of silver nitrate. Similarly, we can have another experiment like barium hydroxide and H2SO4. If you look at the conductance is falling down with the addition of sulfuric acid, and after reaching the equivalence point it is increasing further. So, the overall reaction is the barium hydroxide forming barium sulphate. This barium sulphate is a sparingly soluble salt, do not dissociate into ion significantly. So, they remain almost as a precipitate in the solution. The moment the H2SO4 is added, there is formation of barium sulphate which remain in the solid form and do not contribute much to the conductance. So, there is a fall in the conductance initially. After the complete formation of barium sulphate, there is a further increase in the conductance that can be due to the addition of H2SO4 which have a 2H plus ion which is coming in the solution, and this method can be used to find the concentration of unknown given solution. One of the important titration, conductivity titration is displacement titration, in which the sodium acetate is taken and HCl is added. If you look at what happens to the conductance, you can see that there is an increase in conductance, and after reaching certain point it further increases. So, basically you have a weak acid salt and a strong acid. So, the acetate ion is being replaced by H plus ion, and which increases the conductance to a certain level, but after the consumption of acetate ion, the replacement in a true way, the HCl increases the conductance to a very higher level. Similarly, if we have a salt of weak base ammonium chloride and a strong base like NaOH, there is a fall in the conductance up to a certain level and then it goes up. So, NH4 ion is replaced by the Na plus ion, and which bring about this change in the conductance. After reaching certain point, there is a further increase in the conductance which can be seen from this. So, basically one ion is replacing the second ion, and due to their difference in the mobility, they bring about this change which can be easily monitored using conductivity measurement. If you try to look at the another important application is the solubility product or sparingly soluble salts. What is solubility product? It is a maximum product of the ionic concentration or activity of an electrolyte that at one temperature can continue in equilibrium with the undissolved phase. If we put in a simple words that if a sparingly soluble salt is present with its saturated solution, there is going to be equilibrium between the ions which are in dissolved form or the undissociated electrolyte, and that equilibrium bring about this solubility product. There are various salts like silver chloride, barium sulphate, lead sulphate, etc., which are sparingly soluble, and in water their solubility is so less that it cannot be detected by any common methods. So, conductivity measurement come to its rescue and help us in finding the ions which is dissolved in such a small amount. How this can be done? Like we are interested in finding the solubility product of silver chloride. So, silver chloride is taken in a beaker where it has to be washed with number of times with conductivity water, so that it is free from any type of impurity, soluble impurity, and then it bring down the temperature to room temperature and conductance is being measured for such type of solution, and we get a conductance from those solutions, and finally we have to find the solubility of those solution. It can be done if you look at this expression. The solubility is basically the concentration of the ions which are in dissolved form, and they are so less in the amount. So, C can be replaced by S, and we can look at this expression lambda infinity, because it is so dilute that we can replace the lambda by lambda infinity, and we by simple calculation we can get the solubility from this expression. Lambda infinity is already known for AgCl. Specific conductance has to be determined for the given solution, and we are in position to determine the solubility of the silver ion in the solution. For an example, if lambda infinity is 138.3 Simon meter square per mole at 25 degree Celsius for AgCl, and the kappa is major conductance into cell constant, we can find out the Ksp of the silver chloride. Looking forward, what further can be done with this conductivity measurement? There is ionic product of water Kw, which can be determined. And what is ionic product? It is a product of the concentration of hydrogen and the hydroxyl ion expressed in moles per dm cube, in known as ionic product of water. This is simply a multiplication of these two terms, these two ions, and this value can be determined at different temperature. We will try to look at how it is being done. The specific conductance of the purest water at 25 degree Celsius is found to be 5.54 into 10 raised to minus 6 Simon meter inverse. This is the value of the conductance of a conductivity water, which is a purest form of the water. The conductance of 1 meter cube of water therefore will be 5.54 into 10 raised to minus 6 Simon per meter multiplied with 1 meter cube, which lead to the unit of Simon meter square. There is no change in the numbers. The molar conductance of the water, if it is completely ionized to give 1 mole of H plus ion and 1 mole of OH minus ion, is obtained by adding the molar conductance. We are using the Kohlrausch law to get the lambda infinity, because these two terms are known from literature. Molar conductance of water can be determined using the Kohlrausch law. That is, we can add the two values of lambda infinity of H plus and OH minus, like 349.8 plus 198.5 into 10 raised to minus 4, which lead to a value of 588.3 into 10 raised to minus 4 Simon meter square per mole. So, using Kohlrausch law we can get this value quite easily, and when we know that 1 mole of the hydrogen ion and 1 mole of hydroxyl ion of 1 meter cube of water can give me 5.54 into 10 raised to minus 6 Simon meter square conductance. Naturally, I am in position to find out the concentration of hydrogen ion as well as OH minus ion by taking the ratio of these two terms, 5.54 into 10 raised to minus 6 divided by 548.3 into 10 raised to minus 4, which lead to a value of 1.01 into 10 raised to minus 4 Simon meter square. And when we try to convert into dm cube, we get a value of 1.01 into 10 raised to minus 7 mole per dm cube. As we know that the concentration of H plus and OH minus has to be equal in the water. So, we can put these values there and we get the ionic product of water, which is 1.02 into 10 raised to minus 14, which matches very well with the literature value. In today's lecture, we are able to discuss the probable application of conductivity measurements, especially the conductometric titration, which is relevant for different types of cases: strong acid, weak acid, weak base, and such type of permutation combination of acid and base. So, neutralization reaction can be easily be covered or studied using the conductometric titration, as well as we looked at the precipitation titration, which can be used to find the concentration of given unknown solution, and solubility product which can be determined only through the conductivity measurement, because there is no other chemical method which can find out the solubility and finally the solubility product of the sparingly soluble salt. And we looked at the ionic product of water, find out the value of that. With this we come to the end of this lecture series on electrochemistry 1. In this lecture series we have covered the various topic related with conductance, types of conductance, their how we can control it, how we can have the understanding of theories, we have the different methods we looked at to study different type of conductance. In this lecture series we have covered different topics related with the conductance. We have looked at specific conductance, equivalent conductance, the application of this conductance and their measurement. We have covered the various topics like transport number, the theories which can explain the behavior of conductance, strong and weak electrolyte, and we came to the end with the covering the application of this conductometry measurement by looking at different probable